My dear students, hello. I welcome you all in our series of lectures on cybersecurity. In the previous lecture, we studied about various controls of information security management. Today, we are going to discuss further on information security management. Specifically, we will discuss what is the purpose of information security management. So, let us start with it. Managing computer and network security programs has become an increasingly difficult and challenging job. Dramatic advances in computing and communications technology during the past 5 years have redirected the focus of data processing from the computing center to the terminals in individual offices and homes. The result is that managers must now monitor security on a more widely dispersed level. These changes are continuing to accelerate, making the security manager's job increasingly difficult. The information security manager must establish and maintain a security program that ensures three requirements: the confidentiality, integrity, and availability of the company's information resources. Some security experts argue that two other requirements may be added to these three: utility and authenticity. In this discussion, however, the usefulness and authenticity of information are addressed within the context of the three basic requirements of security management. Number 1, confidentiality. Confidentiality is the protection of information in the system so that unauthorized persons cannot access it. Many believe this type of protection is of most importance to military and governmental organizations that need to keep plans and capabilities secret from potential enemies. However, it can also be significant to businesses that need to protect proprietary trade secrets from competitors or prevent unauthorized persons from accessing the company's sensitive information, for example, legal, personal or medical information. Privacy issues, which have received an increasing amount of attention in the past few years, place the importance of confidentiality on protecting personal information maintained in automated systems by both government agencies and private sector organizations. Confidentiality must be well defined, and procedures for maintaining confidentiality must be carefully implemented, especially for standalone computers. A crucial aspect of confidentiality is user identification and authentication. Positive identification of each system user is essential to ensuring the effectiveness of policies that specify who is allowed access to which data items. Now, the various threats to confidentiality. Confidentiality can be compromised in several ways. The most commonly encountered threats to information confidentiality are due to hackers, masqueraders, unauthorized user activity, unprotected downloaded files, local area networks, and Trojan horses. Let us discuss them one by one. Number 1, hackers. A hacker is someone who bypasses the system's access controls by taking advantage of security weaknesses that the system's developers have left in the system. In addition, many hackers are adept at discovering the passwords of authorized users who fail to choose passwords that are difficult to guess or not included in the dictionary. The activities of hackers represent serious threats to the confidentiality of information in computer systems. Many hackers have created copies of inadequately protected files and placed them in areas of the system where they can be accessed by unauthorized persons. Number 2, masqueraders. A masquerader is an authorized user of the system who has obtained the password of another user and thus gains access to files available to the other user. Masqueraders are often able to read and copy confidential files. Masquerading is a common occurrence in companies that allow users to share passwords. Number 3, unauthorized user activity. This type of activity occurs when authorized system users gain access to files that they are not authorized to access. Weak access control often enable unauthorized access, which can compromise confidential files. Number 4, unprotected downloaded files. Downloading can compromise confidential information if, in the process, files are moved from the secure environment of a host computer to an unprotected microcomputer for local processing. While on the microcomputer, unattended confidential information could be accessed by authorized users. Number 5, local area networks. Local area networks present a special confidentiality threat because data flowing through a LAN can be viewed at any node of the network, whether or not the data is addressed to that node. This is particularly significant because the unencrypted user IDs and secret passwords of users logging onto the host are subject to compromise as this data travels from the user's node through the LAN to the host. Any confidential information not intended for viewing at every node should be protected by encryption. Number 6, Trojan horses. Trojan horses can be programmed to copy confidential files to unprotected areas of the system where they are unknowingly executed by the users who have authorized access to those files. Once executed, the Trojan horse becomes resident on the user system and can routinely copy confidential files to unprotected resources. Next is various confidentiality models. Confidentiality models are used to describe what actions must be taken to ensure the confidentiality of information. These models can specify how security tools are used to achieve the desired level of confidentiality. The most commonly used model for describing the enforcement of the confidentiality is the Bell-LaPadula model. It defines the relationships between objects and subjects. The relationships are described in terms of the subject's assigned level of access or privilege and the object's level of sensitivity. In military terms, these would be described as the security clearance of the subject and security classification of the object. Subjects access objects to read, write, or read and write information. The Bell-LaPadula model enforces the lattice principle, which specifies that subjects are allowed write access to objects at the same or higher level as the subject, read access to objects at the same or lower level, and read write access to only those objects at the same level as the subject. This prevents the ability to write higher classified information into a lower classified file or to disclose higher classified information to a lower classified individual. Because an object's level indicates the security level of data it contains, all the data within a single object must be at the same level. This type of model is called flow model because it ensures that information at a given security level flows only to an equal or higher level. Another type of model that is commonly used is the access control model, which organizes a system into objects, subjects, and operations. A set of rules specifies which operations can be performed on objects by which subjects. This type of model has the additional benefit of ensuring the integrity of information as well as the confidentiality. The flow model supports only confidentiality. Next, requirement for security management is integrity. Integrity is the protection of system data from intentional or accidental unauthorized changes. The challenge of the security program is to ensure that data is maintained in the state that users expect. Although the security program cannot improve the accuracy of the data that is put into the system by users, it can help ensure that any changes are intended and correctly applied. An additional element of integrity is the need to protect the process or program used to manipulate the data from unauthorized modification. A critical requirement of both commercial and government data processing is to ensure the integrity of data to prevent fraud and errors. It is imperative, therefore, that no user be able to modify data in a way that might corrupt or lose assets or financial records or render decision making information unreliable. Examples of government systems in which integrity is crucial include air traffic control systems, military fire control systems, and social security and welfare systems. Examples of commercial systems that require a high level of integrity includes medical prescription systems, credit reporting systems, production control systems, and payroll systems. As with the confidentiality policy, identification and authentication of users are key elements of the information integrity policy. Integrity depends on the access control. Therefore, it is necessary to positively and uniquely identify all persons who attempt access. Next is protecting against threats to integrity. Like confidentiality, integrity can be compromised by hackers, masqueraders, unauthorized user activity, unprotected downloaded files, LANs, and unauthorized programs, for example, Trojan horses and viruses, because each of these threats can lead to unauthorized changes to data or programs. For example, authorized users can corrupt data and programs accidentally or intentionally if their activities on the system are not properly controlled. Three basic principles are used to establish integrity controls. Number 1, granting access on a need to know basis. Number 2, separation of duties. Number 3, rotation of duties. Let us discuss each of them one by one. Number 1, need to know access. Users should be granted access only to those files and programs that they need in order to perform their assigned job functions. User access to production data or source code should be further restricted through use of well-formed transactions, which ensure that users can change data only in controlled ways that maintain the integrity of the data. A common element of well-formed transactions is a recording of data modifications in a log that can be reviewed later to ensure that only authorized and correct changes were made. To be effective, well-formed transactions must ensure that data can be manipulated only by a specific set of programs. These programs must be inspected for proper construction, installation, and controls to prevent unauthorized modification. Because users must be able to work efficiently, access privileges should be judiciously granted to allow sufficient operational flexibility. Need to know access should enable maximum control with minimum restrictions on users. The security program must employ a careful balance between ideal security and practical productivity. Number 2, separation of duties. To ensure that no single employee has control of a transaction from beginning to end, 2 or more people should be responsible for performing it. For example, anyone allowed to create or certify a well-formed transaction should not be allowed to execute it. Thus, a transaction cannot be manipulated for personal gain unless all persons responsible for it participate. Number 3, rotation of duties. Job assignments should be changed periodically so that it is more difficult for users to collaborate to exercise complete control of a transaction and subvert it for fraudulent purposes. This principle is effective when used in conjunction with separation of duties. Problems in effectively rotating duties usually appear in organizations with limited staff resources and inadequate training programs. Next is various integrity models. Integrity models are used to describe what needs to be done to enforce the information integrity policy. There are 3 goals of integrity which the model addresses in various ways. Number 1, preventing unauthorized users from making modifications to data or programs. Number 2, preventing authorized users from making improper or unauthorized modifications. Number 3, maintaining internal and external consistency of data and programs. The first step in creating an integrity model for a system is to identify and label those data items for which integrity must be ensured. Two procedures are then applied to these data items. The first procedure verifies that the data items are in a valid state, that is, they are what the users or owners believe them to be because they have not been changed. The second procedure is a transformation procedure or well-formed transaction which changes the data items from one valid state to another. If only a transformation procedure is able to change data items, the integrity of the data is maintained. Integrity enforcement systems usually require that all transformation procedures be logged to provide an audit trail of data item changes. Another aspect of preserving integrity relates to the system itself rather than only the data items in the system. The system must perform consistently and reliably, that is, it must always do what the users or owners expect it to do. There are various integrity models that suggest different approaches to achieving integrity. We will discuss them one by one. Number 1, the BIBA model. The first model to address integrity in computer systems was based on a hierarchical lattice of integrity levels defined by BIBA in 1977. The BIBA integrity model is similar to the Bell-LaPadula model for confidentiality in that it uses subjects and objects. In addition, it controls object modification in the same way that Bell-LaPadula controls disclosure. BIBA's integrity policy consists of 3 parts. The first part specifies that a subject cannot execute objects that have a lower level of integrity than the subject. The second part specifies that a subject cannot modify objects that have a higher level of integrity. The third part specifies that a subject may not request service from subjects that have a higher integrity level. Number 2, the Gauguin model. The Gauguin model, published in 1982, is based on the mathematical principle governing automatons and includes domain separation. In this context, a domain is the list of objects that a user can access. Users can be grouped according to their defined domains. Separating users into different domains ensures that users cannot interfere with each other's activities. In addition, the system contains information not related to permissions, example, user programs, data and messages. The combination of all this information is called the state of the system. The automaton theory used as a basis for this model predefines all of the states and transitions between states, which prevents unauthorized users from making modifications to the data or programs. Number 3, the Sutherland model. The Sutherland model, published in 1986, approaches integrity by focusing on the problem of inference, that is, the use of covert channels to influence the results of a process. This model is based on a state machine and consists of a set of states, a set of possible initial states and a transformation function that maps states from the initial state to the current state. Although the Sutherland model does not directly invoke a protection mechanism, it contains access restrictions related to subjects and information flow restrictions between objects. Therefore, it prevents unauthorized users from modifying data or programs. Number 4, the Clark-Wilson model. The Clark-Wilson model, published in 1987 and updated in 1989, involves 2 primary elements for achieving data integrity: the well-formed transaction and separation of duties. Well-formed transactions, as previously mentioned, prevent users from manipulating data, thus ensuring the internal consistency of data. Separation of duties prevents authorized users from making improper modifications, thus preserving the external consistency of data by ensuring that data in the system reflects the real world data it represents. The Clark-Wilson model differs from the other models that are subject and object oriented by introducing a third access element, programs, resulting in what is called an access triple, which prevents unauthorized users from modifying data or programs. In addition, this model uses integrity verification and transformation procedures to maintain internal and external consistency of data. The verification procedures confirm that the data conforms to the integrity specifications at the time the verification is performed. The transformation procedures are designed to take the system from one valid state to the next. The Clark-Wilson model is believed to address all the three goals of integrity. Number 5, the last model is the Breuer-Nash model. The Breuer-Nash model, published in 1989, uses basic mathematical theory to implement dynamically changing access authorizations. This model can provide integrity in an integrated database. In addition, it can provide confidentiality of information if the integrated database is shared by competing companies. Subjects can access only those objects that do not conflict with standards of fair competition. Implementation involves grouping data sets into discrete classes, each class representing a different conflict of interest. For example, classified information about a company is not made available to a competitor. Assuming that a subject initially accesses a data set in each of the classes, the subject would be prevented from accessing any other data set in each class. This isolation of data sets within a class provides the capability to keep one company's data separate from a competitor's in an integrated database, thus preventing authorized users from making improper modifications to data outside their purview. Now, the next and the last requirement for security management is availability. Availability is the assurance that a computer system is accessible by authorized users whenever needed. Two facets of availability are typically discussed. Number 1, denial of service. Number 2, loss of data processing capabilities as a result of natural disasters. For example, fires, floods, storms or earthquakes, or human actions, for example, bombs or strikes. Denial of service usually refers to actions that tie up computing services in a way that renders the system unusable by authorized users. The loss of data processing capabilities as a result of natural disasters or human actions is perhaps more common. Such losses are countered by contingency planning, which helps minimize the time that a data processing capability remains unavailable. Contingency planning, which may involve business resumption planning, alternative site processing or simply disaster recovery planning, provides an alternative means of processing, thereby ensuring availability. Physical, technical and administrative issues are important aspects of security initiatives that addresses availability. The physical issues include access controls that prevent unauthorized persons from coming into contact with computing sources, various fire and water control mechanisms, hot and cold sites for use in alternative site processing, and off-site backup storage facilities. The technical issues include fault tolerance mechanisms, for example, hardware redundancy, disk mirroring and application checkpoint restart, electronic vaulting, that is automatic backup to a secure off-site location, and access control software to prevent unauthorized users from disrupting services. The administrative issues include access control policies, operating procedures, contingency planning and user training. Although not obviously an important initiative, adequate training of operators, programmers and security personnel can help avoid many computing stages that result in the loss of availability. In addition, availability can be restricted if a security office accidentally locks up an access control database during routine maintenance, thus preventing authorized users access for an extended period of time. Considerable effort is being devoted to addressing various aspects of availability. For example, significant research has focused on achieving more fault-tolerant computing. Another sign that availability is a primary concern is that increasing investments are being made in disaster recovery planning combined with alternative site processing facilities. With this, our today's lecture is over. Today, we learned about the three basic purposes of security management, such as integrity, confidentiality and availability. Whether a system emphasizes one or the other of these purposes depends on the functions performed by the applications. Historically, confidentiality has received the most attention, probably because of its importance in military and government applications. As a result, capabilities to provide confidentiality in computer systems are considerably more advanced than those providing integrity or availability. Significant research efforts have recently been focused on the integrity issue. Still, little attention has been paid to availability, with the exception of building fault tolerance into vendor products and including hot and cold sites for backup processing and disaster recovery planning. I hope you understood today's lecture. In the next lecture, we will discuss about some other security concepts. Till then, goodbye.